We throw around words like probably all the time, don't we? Like it'll probably rain or, high probability of traffic.
Yeah.
But what does that really mean underneath? We live in this world just full of uncertainty, and well, today we're diving deep into how we actually make sense of it. It's the framework. Probability.
That's exactly right. I mean, it's everywhere. From figuring out, what's likely for dinner to much bigger things like assessing risks with new tech. Probability is always there.
It's the math trying to quantify chances.
Quantify the odds.
So for this deep dive, we've got some really interesting material that kind of lays out the basics of probability. And our mission really is to properly understand these core ideas, to get past just saying likely or unlikely and really get the concepts.
Yeah, build that foundation.
We'll be looking at the basic language stuff like experiments, random experiments, sample spaces, what equally likely means, defining an event.
And then how we measure it.
Right. How we actually measure probability, both the theory and, how it works in practice. We'll touch on things that are definite, things that are impossible, using simple examples like coins and dice, maybe some cards too.
Exactly. It's all about getting a solid handle on how we think about chance.
Okay, so let's start with the real basics. Our sources define an experiment as, well, any process that gives you a well-defined outcome.
Well-defined being key.
Yeah. Like think about flipping a coin. You get heads or you get tails, clear result. Or rolling a standard die, you'll get a number, 1 through 6. Again, well-defined.
And you need to know those possible results before you start. Now, building on that is the idea of a random experiment. This is where it gets, interesting.
Let's go so.
Because while we know all the possible outcomes ahead of time, we can't actually predict the specific one for any single try.
Right. So the coin flip, we know it's heads or tails, but before the flip, no idea which one.
Exactly.
Same for the die. We know it's 1, 2, 3, 4, 5, or 6. But which number comes up, you don't know till you roll it.
And these experiments, they can have, 2 outcomes or many, many more.
Okay, so how do we keep track of all these possibilities?
That's where the sample space comes in. It's basically just a complete list, everything that could happen in a random experiment. We usually write it as a capital S.
Okay, so for just one coin toss, the sample space S is just HT, heads, tails. Simple enough? And for rolling one die, S would be 1, 2, 3, 4, 5, 6. Still pretty straightforward.
Right.
But it gets more complex with multiple things happening, yeah. Like what if we toss 2 coins?
Good question. So now you have to think about combinations. First coin, heads or tails. Second coin, also heads or tails.
Okay.
So you can get heads on both, HH, or heads on the first, tails on the second, HT, or tails, then heads, TH, or tails on both, TH.
Oh, so 4 possibilities.
Exactly 4. So the sample space S, H, H, T. And notice, like HT is different from TH. The order matters here. It tells you which coin did what.
Okay, yeah, that makes sense. The order counts. And rolling 2 dice. Wow, that sample space must get huge.
It does. It jumps to 36 outcomes. Our materials show them all listed out as pairs, 1, 1, 1, 2, all the way to 6.
36. Wow. And again, order matters. So 1, 2 is different from 2, 1.
Precisely. First die, second die. They're distinct results.
Got it.
And maybe one more quick one. Toss a coin, then roll a die. The sample space combines them, right? So you'd have H1, H2, H3 up to H6, and then T1, T2 up to T6. 12 possibilities in total there.
Okay, that really maps it out clearly. Now, the sources also talk about equally likely outcomes. That sounds, well, it sounds like what it is, right?
It's pretty intuitive, yeah. It just means every possible individual outcome in that sample space has the exact same chance of happening.
Like a fair coin. Heads and tails have the same shot.
Exactly. Or a fair die. Each number, 1 through 6, has an equal chance of landing face up. 1 out of 6.
But what about when they're not equally likely?
Right. So imagine a bag. It's got, say, 6 red balls and only 2 yellow ones. You reach in, pull one out. The outcome is either red or yellow.
Okay.
But they aren't equally likely, are they? You're much more likely to grab a red one. Why? Just because there are more of them.
So the number of each type matters.
Fundamentally, yes. If you have the same number of each possible type of outcome, then they're equally likely, like 1 head, 1 tail, or 1 of each number on a die.
That makes perfect sense.
Okay.
Okay, so we've got experiments, random ones, the sample space listing everything and whether those things are equally likely. What exactly is an event then in probability terms?
An event is, well, it's basically just an outcome or maybe a set of outcomes that you're interested in. Something that happens as part of your random experiment.
Okay.
So, tossing a coin, getting a head, that's an event. Rolling a die, rolling a 3 is an event. Drawing the ace of spades, Also an event. It's just a specific result or collection of results from the sample space.
Right. It's the particular thing we're looking for within all the possibilities. So now that we know what could happen in the sample space and what we're looking for the event, how do we actually, measure the chance? How likely is it?
That's probability itself. We usually write it as PE, the probability of event E happening.
P for probability, E for event. Makes sense.
And the basic way to calculate it, what our sources focus on, is this. You take the number of outcomes that count as your event E. We call these favorable outcomes.
Favorable meaning they match what we're looking for.
Exactly. And you divide that by the total number of all possible outcomes in the sample space.
Okay.
So the formula is PE, number of favorable outcomes. Total number of possible outcomes, often just written M over N.
No. Okay. Let's use an example. Rolling a standard die once. What's the probability of getting an even number?
Okay, good one. So our event E is rolling an even number. What are the favorable outcomes here?
2, 4, and 6.
Right. So the number of favorable outcomes, M, is 3. And what's the total number of possible outcomes when you roll a die?
6. Numbers 1 through 6. So N is 6.
Perfect. So P even MN equals 36.
Yeah.
Which simplifies.
To 1/2. 12.
Exactly. So there's a 1 in 2 chance of rolling an even number.
Got it. So probability is basically this ratio,
Yeah.
what we want, divided by what's possible. Now, our materials mentioned different kinds of probability, empirical and classical.
Yeah, that's right. So empirical probability, sometimes called experimental probability, is all about observation. You actually do the experiment maybe many times.
Like actually flipping a coin 100 times.
Exactly. You flip it 100 times, you count how many heads, how many tails. Let's say you get, 57 heads and 43 tails.
Okay.
Your empirical probability of getting a head based on that specific experiment would be 57 out of 100, or 0.57. And for tails, 43 out of 100, or 0.43.
So it's based on what you actually saw happen.
Precisely. But, and this is important, it's an estimate. If you did another 100 flips, you might get, 52 heads or 49. It can vary. It's really useful when the theory is hard to figure out.
Okay. Learning from doing makes sense. So what about the other one? Classical probability.
Classical or theoretical probability is what we've mostly been doing so far. You calculate it without doing the experiment.
Oh, yeah.
It works when you can assume that all the individual outcomes in your sample space are equally likely, like our fair coin or fair die.
Right.
And the formula is just the one we used. Number of favorable outcomes divided by the total number of outcomes. Our sources make it clear this theoretical classical type is the main focus for this deep dive.
Okay, great. So let's really nail this classical probability down with some more examples from the material. First one's basic. Probability of getting ahead when you toss a fair coin just once.
Right. Dead simple. Favorable outcome. Getting ahead, that's one outcome. Total possible outcomes. Heads or tails, that's 2 outcomes. So, probability of heads, PH, is 1 divided by 2, 1/2.
And the material calls an event with just one favorable outcome, like this, an elementary event.
Yeah, that's the term they use. Elementary event. Simple outcome.
Okay, next example, a bag. It's got one black ball, one red ball, one green ball. Assume they're all identical otherwise, so equally likely to be picked.
Right.
What's the probability of drawing each color?
Okay, 3 balls total, right? Black, red, green. So 3 total possible outcomes,
Yep.
and they're equally likely. So probability of drawing the red one, well, there's 1 red ball, so
Yeah.
1 favorable outcome out of 3 total. P red, 13.
And the same for black and green.
Exactly the same. P black, 13, P green equals 13.
And look, if you add those up, 13 plus 13 plus 13.
They get 33, which is 1. And that's a key point. The sum of the probabilities of all the possible elementary events, all the distinct single outcomes in any experiment, has to add up to 1. It covers all the possibilities.
That's a neat check. Useful.
Well,
Okay, back to the single die roll. Standard 6-sided die. Probability of rolling a number greater than 2.
okay, greater than 2. Which numbers are those on a die?
3, 4, 5, and 6
Right. So that's 4 favorable outcomes.
out of 6 total possibilities.
Exactly. So the probability is 46, which
Thanks,
simplifies too.
2/3, 23.
Correct. Now, what about the probability of getting a number less than or equal to 2?
Less than or equal to 2. That's just 1 and 2.
So 2 favorable outcomes this time,
Still out of 6 total, so 26.
which is 13.
Yeah.
Okay, now here's a slightly different phrasing. Probability of getting a number not greater than 2.
Not greater than 2. Which numbers are those?
Well, that's also just 1 and 2 again, isn't it?
It is. So it's the exact same set of favorable outcomes, 2 of them, which means the probability is also 26 or 13.
Right, so less than or equal to 2 and not greater than 2 mean the same thing here.
In this specific case, yes.
And this leads into something the material calls complementary events.
Yeah.
Right? If E is the event getting a number greater than 2,
which we found had a probability of 23.
then the event not getting a number greater than 2 is its complement, often written as not E, or sometimes E with a bar over it.
Overline, yeah, that's the notation.
And we just found the probability of that event, overline is 13. And notice, 23 plus 13 equals 1.
Exactly. That's the core idea of complementary events. They are like mutually exclusive opposites. If one happens, the other can't. And together, they cover all the possibilities.
So one of them has to happen.
Right. And because of that, their probabilities always add up to 1 PE plus P overline 1. Always.
Which is super useful. It means if you find the probability of something happening, PE, it's easy to find the probability of it not happening. Just do 1 minus PE.
Precisely. PE, not E, equals 1 PE. It's a great shortcut sometimes.
Definitely a tool to keep in mind. Okay, let's switch gears. Playing cards. Standard deck, 52 cards, well shuffled. You draw 1 card. What's the probability it's a face card?
Okay, first step. How many face cards are there?
Kings, queens, jacks.
Right?
Yep.
And there are 4 suits, spades, hearts, diamonds, clubs.
So a king, queen, and jack in each suit. That's 3 face cards per suit times 4 suits is 12 face cards.
You got it. 12 favorable outcomes. And the total number of cards in the deck.
52.
So the probability of drawing a face card is 12 favorable outcomes divided by 52 total outcomes. P, face, equals 1,252.
Can we simplify that? Both are divisible by 4.
They are. 12 divided by 4 is 3. 52 divided by 4 is 13. So it simplifies to 313.
313 chance of getting a face card.
Yeah.
Now, what's the probability of not drawing a face card?
Well, we could count them directly. If there are 52 total cards and 12 are face cards, how many are not face cards?
52 minus 12 is 40.
Right. So 40 non-face cards, the probability is 40/52.
Which also simplifies. Divide by 4 again, gives 713.
Correct. Or we could use our new trick, the complement.
P not face card should be 1 minus P face card.
Exactly, which is 1 minus 313.
Common denominator is 13, so that's 1313 minus 313 equals 313. Same answer.
See, complementary events are handy. And yeah, the material reminds us about the deck structure. 4 suits, 13 cards each. The face cards, the colors, all that basic card knowledge helps here.
Definitely useful background. Okay, different scenario. Badminton match. Rajesh versus Joseph. We're told the probability of Rajesh winning is 0.58. Assuming no draws are possible, what's the probability Rajesh doesn't win, and what's the probability Joseph wins?
Okay, if P Rajesh wins equals 0.58, then the probability he doesn't win is the complement.
Must be. So 1 minus 0.58.
Just 0.42.
Okay. Yeah.
So P Rajesh doesn't win equals 0.42.
And since the problem says someone has to win, if Rajesh doesn't win.
Joseph must win. They're the same event in this context. So P Rajesh wins is also 0.42.
Makes sense. Okay, back to our trusty die roll one last time.
Yeah.
Single roll. Probability of rolling a 7.
A 7 on a standard 6-sided die.
Yeah.
Well, the faces are numbered 1, 2, 3, 4, 5, 6. There's no 7.
Right.
So the number of favorable outcomes rolling a 7 is 0.
Okay. 0 favorable outcomes.
Out of 6 total possible outcomes. So the probability is 0.6, which is just 0.
What's the probability of 0.
Yep. And our material calls this an impossible event. It literally cannot happen.
Okay. Impossible event equals probability 0. Now, flip side. What's the probability of rolling a number less than 7?
Less than 7. Okay, let's look at the outcomes. 1, 2, 3, 4, 5, 6. Are they all less than 7?
Yeah, all 6 of them are.
So in this case, all 6 possible outcomes are favorable outcomes.
So the probability is 6 favorable out of 6 total. 66.
Which equals 1.
Probability of 1.
And this is called a certain event or a sure event. It's guaranteed to happen every single time you roll the die.
Okay, so we've seen probabilities of 0 impossible and 1 certain, and everything else seems to fall in between.
That's the fundamental rule. For absolutely any event, E, its probability, PE, has to be somewhere between 0 and 1 inclusive. It can be 0, it could be 1, or anything in between.
So $0 the pull, it can never be negative. Or bigger than 1.
Never. That's a crucial check. If you calculate a probability and get like 1.2 or negative 0.1, you know you've made a mistake somewhere.
Good tip. Now, the sources also talk about what happens when we do things multiple times, right? Like tossing a coin more than once.
Yes. This is where tracking outcomes gets a bit more involved.
So toss a coin once. 2 outcomes. HD. That's 2 and the $1 out.
Yeah.
Toss it twice, or toss 2 coins at once. If that gives $22 equals 4, 1 pry comes. HH, HT, TH, TT.
Right. And the order mattered in the sequence, HT vs TH.
And if you toss it 3 times, Or 3 coins together.
Then it doubles again. 23 Weckels, 8 8-hour possible outcomes. You'd have HHH, HHT, HTHH, and then HDT, TTT, HTDT.
8 different sequences.
Exactly. And the key point the material makes is that doing it 3 times in a row gives the same set of possible outcomes as doing 3 at the same time. The total number of possibilities is the same.
Okay, and the general rule seems to be toss n coins, or 1 coin n times. You get 2 anomalous possible outcomes.
That's the pattern. And the same logic works for dice. Roll 1 die, $61 equals 6 outcomes.
Roll 2 dice or 1 die twice. We said that was $62 equals 366 outcomes, those ordered pairs.
Correct. And again, rolling 2 dice together gives the same 36 possibilities as rolling 1 die, then rolling it again.
And the general rule for dice would be roll in dice, or 1 die in times, you get $60 outcomes.
Precisely.
Yeah.
Understanding how these possibilities multiply, how they grow exponentially, is really fundamental when you deal with multiple trials.
Okay, let's put that 62 36C outcomes thing to work. Example, throw 2 standard dice together. What's the probability both dice show the same number?
Okay. Total outcomes equals 36. We know that. Now, which outcomes have the same number on both dice?
1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. How many is that?
That's 6 of them. 6 favorable outcomes.
Right, so the probability is 6 favorable out of 36 total. 636.
Which simplifies to 16.
Correct. 1 chance in 6.
Okay, same setup. 2 dice. Probability the first die shows a 6. The second die can be anything.
Okay, first die is 6, so the pairs would be 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6.
That looks like 6 outcomes again.
It is. 6 favorable outcomes where the first die is a 6, still out of 36 total. So 636 again.
Also 16. Interesting. Right, next one. Probability the sum of the numbers on the 2 dice is 9. Okay, the sum needs to be 9. Let's think. How can we make 9 with 2 dice? You could have a 3 on the first and a 6 on the second. 3, 6. Or 4, 5.
Or the other way around. 5, 4.
Yep. And 6, 3.
Is that it? Can't use 1 or 2.
Nope. That seems to be all of them. So 3, 6, 4, 5, 5, 4, 6, 3. How many pairs is that?
4 pairs. 4 favorable outcomes.
Out of 36 total. So 436.
Simplify that. Divide by 4 gives 19.
Probability is 19. Correct.
Okay, how about the probability that the product of the 2 numbers is 8?
Product equals 8. Okay, thinking. How do you multiply to get it? 2 times 4. So 2.
When the reverse, 4, 2.
Yep. Anything else? 1 times 8 isn't possible on a die. 3 doesn't work. 5, 6 don't work.
Looks like just those 2. 2, 4, and 4, 2.
Right. Only 2 favorable outcomes this time.
Still out of 36 total, so 236.
Which simplifies to 118.
118. Quite unlikely. Okay, last one for the 2 dice. Probability the total sum is greater than 9.
Greater than 9. So sums of 10, 11, or 12. Let's list them. Sum of 10. 4, 6, 5, 6, 4. That's 3.
Sum of 11. 5, 6, and 6. 5, so that's 2 more.
And sum of 12. Only one way.
6, 6.
Okay, so that's 3 plus 2 plus 1 equals 6 favorable outcomes in total.
Yep. 6 outcomes give a sum greater than 9 out of 36 total, so 636 again.
Which is 16. Same probability as getting doubles, or the first die being a 6. Interesting how these things work out.
It is indeed.
Wow. Okay, so yeah, we've really gotten into the weeds of basic probability here. We started just noticing how much we talk about chance, you know.
And then we really broke it down, looked at the core ideas. What's an experiment? What makes it random? What's this crucial sample space idea?
And when outcomes are equally likely, defining an event. And critically, that basic formula for classical probability. Favorable over total.
Right. We also touched on the difference between that theoretical classical probability and the empirical kind you get from, like, actually doing the experiment.
And work through quite a few examples, coins, dice, cards, to see how it plays out with single events, multiple events. And we saw those edge cases. Impossible events with probability 0, certain events with probability 1, and that really useful idea of complementary events adding up to 1.
Yeah.
Ultimately, getting these basics down gives you a really powerful way to think about and quantify uncertainty, which is just everywhere.
It really is.
That's
It's foundational stuff for so many fields, but also just for, everyday thinking.
Absolutely.
So here's something to maybe chew on after this. Now that you've got this clearer idea of basic probability sample spaces, favorable outcomes, calculating chances, how might that actually change how you look at everyday risks or predictions?
Yeah.
Think about those times, big or small, where chance is involved, even if you didn't think about probability explicitly before. Does understanding this foundation maybe shift your perspective just a little? What might you see differently now?